Hello again, Calc students. Today we're going to be looking at section 2.2 involving limits involving infinity. This is the first video of two. I've actually already recorded this video and posted it on Moodle, but some of you have not been able to access that, so we're going to be looking at it here again, and then this will be posted on YouTube. So hopefully I'll be able to keep this under 15 minutes. So taking a look here, the first example we have here is we're looking at limits as x approaches positive and negative infinity. So here we have we're going to find the limit as x approaches infinity of 1 over x. So if we take a look at our function over here, this is the function 1 over x. It's got these, it's not a parabola. I think these are hyperbolas. I think that's the correct word for these symbols. That's what this looks like. So I want to know what happens to the function. What goes on as my x values get bigger and bigger and bigger and bigger? Well, as I think most of you can see from the picture here, if we start at 0 and we get more and more positive, it gets bigger and bigger and bigger, goes to like 1-ish, it goes to 2, and then so as our x's get larger and larger and larger, what happens to our y's? Well, they get smaller and smaller and smaller, but they start to level out. They start to level out here at 0. They start to get closer and closer to 0. If we think about this, let's think about some examples. What happens as x gets bigger and bigger and bigger? Well, if we were to do, say, the f of, just for fun, we'll call it f of 3, we'd have 1/3. If, say, we did f of 10, we would get 1/10. Again, we're plugging in these x values for x here. If we say did f of 1,000, we get 1 over 1,000. So we're getting, as x gets bigger and bigger and bigger, our fractions are getting smaller and smaller and smaller, and they're never actually going to reach 0. But they're getting very, very close to 0. So we're going to say as x gets infinitely big, as x gets closer and closer to infinity, the limit of this is going to be 0. So that's as x approaches positive infinity. Well, what about the limit when x approaches negative infinity? Well, let's take a look here. As our function gets smaller and smaller and smaller, it starts out really, really big when it's close to 0. But then as we get more and more negative, at 1 it starts to get smaller. 2 it's even smaller. 3, 4, and again it starts to level out. It starts to get closer and closer to 0. Let's take a look. Let's take a brief look at what happens for this function when we plug in more and more negative numbers. For example, f of negative 3, we get negative 1 over 3. F of negative 10 be negative 1/10. F of negative 1,000, well, it's negative 1 over 1,000. So as you can see, even though these numbers are negative, they are also getting closer and closer and closer to 0 as we get bigger and bigger and bigger. So we'd say that the limit as x approaches negative infinity of the function 1 over x is also 0. Which, as you can see here, these get closer and closer to 0, but they never touch. They kind of level out. That leveling out is what we call an asymptote. If you take a look at the bottom of page 65, you'll find the formal definition of an asymptote. Let me go and draw this in here. We'll do it in red because red's a nice color to draw graphs in. Now, I may have drawn this a little bit high, but the great thing about computing is you can easily move your lines down just a little bit if you need to. There we go. Alright, so this red line here represents our asymptote. And what this is, if you read at the bottom of page 65, it says, the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit of x approaches infinity of the function is equal to b, or the limit as x approaches negative infinity of the function equals b. Well, in this case, our b, this y equals b, would be the line y, oops, and I should get a pen tool here, y equals 0. So because not only does our positive limit but our negative limit, or go to positive and negative infinity, is 0, we have our asymptote at y equals 0. Now, some of you may have heard asymptotes. They go on and on and on forever, and the lines never actually touch it. Well, that's a little bit of a misconception. You'll see why in a couple examples. But for the time being, that's the definition we're going to be working with. The next example is a true example. If you look at example 1, looking for horizontal asymptotes, I have shown here the graph of f of x equals x over the square root of x squared plus 1, as you see written right over here. And we want to, again, find what happens to this function as x approaches infinity and as x approaches negative infinity. Well, if you want, this has very similar axes as your textbook. My x's actually go from negative 15 to positive 15, but the y's are the same. So, but if we take a look here, as our x's get larger and larger and larger, as we get closer and closer and closer to infinity, this seems to be leveling off at 1. And as we get smaller and smaller and smaller and smaller, and we start to level off, this appears to go to negative 1. So what we really have here is I'm not going to go through all the mathematical steps behind it. For now, I'm going to just assume that you believe me. But as our function approaches positive infinity, the limit of this is going to be equal to 1. And as it approaches negative infinity, it approaches negative 1. So in this case, the limit for positive infinity and negative infinity don't go to the same thing, which means we actually now have 2 asymptotes. Let's go and put those asymptotes in. I'll do that one here. Stick with red. Red's, like I said, a good color for asymptotes. We have a horizontal asymptote at y equals 1, which I'll drop down in just a moment, and 1 at y equals negative 1. And again, the definition of asymptote saying if the limit goes from of a function goes to a certain number at infinity or negative infinity, that is where we'll find an asymptote. So again, notice how both of these functions get really, really close to this, but they should never actually touch. And again, that's just a small misconception, which hopefully we can clear up in just a moment. So we have now found 2 asymptotes for this graph. So again, once more, you find the asymptotes when the limit of a function as x approaches infinity equals some number b. That b would be your asymptote. In this example, b was 1. Or as the limit as x approaches infinity of f of x equals b. And actually, instead of infinity, I should call this negative infinity. Negative infinity, as we see here. That's where we find asymptotes. If you have further questions, you can definitely ask me in class. Last example I want to go over for this video is let's find out what the limit as x approaches infinity of sine of x over x is. If you take a look at the right here, I have the graph shown over here. Now this one is actually is interesting. Notice how as x goes closer and closer to infinity, this kind of it starts out really high, drops down, not quite as low, back up, not quite as high, down and up, down and up. Well, what actually happens here is this, you might say this oscillates. That might not be the exact right term for this, but it oscillates. It goes up and down. And what's going to happen is this is going to get closer and closer and closer to 0. And what I'll do is I will, oh shoot, I wanted to show, okay. Anyway, I'll show that this gets closer and closer and closer to 0. In fact, we'll talk about the sandwich theorem as long as time allows. I got about 5 more minutes left in this. But as you can see here, this gets closer and closer and closer to 0. And you might say, well, Mr. Ganson, what you're saying, it makes sense, but I would like a little bit more solid proof. Well, let's take a look at the table. As you see here, I've put in this function into my y1, and I'm going to specifically set my table, so I hit second. Above this window button is the table set. Yeah, I'm going to start my table at 0, And my change in my table, what my x's are going to go up by, will make it 100. So that's a 4 out of 1. And now let's take a look at our table. So as you can see, as we start at, oops, that was not the one that I wanted. Sine of x over x. Sorry, I didn't have the right function here. Sine of x over x. So now when we look at our table, it is undefined at 0, as we would expect it would be. But as you take a look here, as our numbers get larger and larger and larger, and notice we're doing this actually fairly quickly, they are starting to get closer and closer to 0. Negative 0, 0, negative 0.0051, negative 0.0044, negative 0.0033. They get smaller and smaller and smaller as our x's get larger and larger and larger. So they are getting very, very, very close to 0. Now, I can actually give you a little bit more of a proof behind this using what's called the squeeze theorem. What the squeeze theorem basically says is if we have a function that has its limit approaching a number, and another function whose limit approaches that same number, if there's some function in between those two, well, that one will also have to go to that same number. Consider this. Negative 1 is less than or equal to the sine of x is less than or equal to 1. Those of you who've taken trigonometry may be familiar with that. Just your regular sine function oscillates between negative 1 and 1, but it does not exceed those. And you might be saying, well, why does this matter? I don't really care about the sine of x function. This is the sine of x over x. Well, what happens when I divide each side by x? Well, we already know, and specifically, let's see what happens when we take the limit of each of these. So I really want to know what the limit as x approaches infinity of negative 1 over x. That should, in theory, be less than or equal to the limit as x approaches infinity of sine of x over x. That's less than or equal to the limit as x approaches infinity of 1 over x. So so what I did here is we took this fact here that for now I'm assuming you know is true, divided each part by x, which is a legal move, and now I want to see, well, what happens when I take the limit of each of these? Well, we know some of this stuff. We know that this limit, because we looked at it, we figured it out is 0. And we did that in one of our previous examples. I'm going to assume it's not going to take much work to show that as this function gets bigger and bigger and bigger, as it gets closer and closer to infinity, that this will also approach 0. Well, what about our sine of x function? What happens to this? Well, the limit as x approaches infinity of sine of x over x, well, if this is 0 and this is 0, there is no other choice but for this to also be equal to 0. It has to be. It gets squeezed in between those two. Let me take a look and see how much record time I have left. 1.5 minutes. Okay, I'm going to stop the video for just a moment. And when we return, we have our G-Calc application pulled up. This is an online calculator, but I have 1.20 seconds to go over this. So if we take a look here, the green function, we take a look at our graphs. The red function is the negative 1 over x function. The green function is the 1 over x function, and then the blue function is the sine of x over x function. So as you can see, this sine of x function goes up and down, and it oscillates between the two, but it never passes either one of them. And as you see, it's getting squished between these. If we go take a quick look at the view, I'm going to increase my x max to 100, and we will see what this does to the graph. And as you can see, the green graph, the 1 over x graph gets smaller and smaller and smaller, closer and closer to 0, as does the negative 1 over x graph, gets closer and closer to 0. But the the sine of x over x graph gets squished in between these two very, very carefully. Again, if we take a look at our graphs, these are the colors that correspond with each of these. So, thank you for listening, and this will, obviously, if you're watching, this has been posted. If you have any questions, please ask in class.